thanks. So I will be no exception. I have first to thank the organizers for this very nice conference, which was very exciting. And I want also to thank Ludovic Jobert, who gave his talk, who took on him to give his talk, despite a very nasty Natal aquatic pinch point yesterday evening, I guess. So this is the first living pinch point I've ever seen, anyway. So I will talk about this emergent classical magnetic charge crystal in a frozen Kagome dipolar spin ice. And this is the Huzimi cactus, so which has absolutely nothing to do with the lattice I'm going to speak of, but I like it, so I always put it on the first slide of my slide presentations. So actually, of course, it's a collaboration between many experimentalists and myself. So part of which work in the Institut Néel in Grenoble. So these are my colleagues in Institut Néel, Nicolas Rougemay, Olivier Frichard, and Jean-Christophe Toussaint. Both are experimentalists. And as I should quote Peter Schiffer, who said that chemists are wonderful people, and I guess experimentalists as well are wonderful people. Jean-Christophe Toussaint is a specialist in micromagnetism. In Nancy, in Institut Jean Lamour, all those people are also experimentalists who are specialists in lithography, e-beam lithography, and all this kind of fabrication process. You just draw. I mean, really, you draw something, they print it. So it's really, it's amazing for me. And these people work in synchrotron, Rachid Belkou, El Moussaoui, and I don't know actually the first names. And actually, so Nicolas should have been here to present the result, but he preferred to stay in a cave counting photons and electrons in Electra this week. So I'm here on behalf of this guy. And this work was published recently this year. So this is the outline of my talk. I will first briefly mention general motivation, a short historical background and issues. And I will take the opportunity of this general motivation to give you an example of a classical Heisenberg antiferromagnet which has pinch point. So just to make the point that it's not pinch point or not, and the Coulomb phases are not at all restricted to discrete-like frustrated Ising ferromagnet. Of course, maybe it's obvious for many of you, but maybe not for everyone. And then I will say a few stuff about how you can visualize the physics. Then a few words also about our study, and I will conclude with and give perspectives, and maybe to add another kind of monopause, which will not only be Z2, but which would have maybe another degree of freedom, a micromagnetic one. So classical physics is interesting. Even if there is no quantum fluctuation, it's still interesting. So you know, for instance, the triangular and the Kagome single-axis Ising antiferromagnets, they have an extensive degeneracy. I mean, a massive degeneracy. Entropy is always extensive, but it's a massive degeneracy, and they are strongly correlated, but disordered magnets. And one way to show the richness of this classical physical world, it may be to show an example among those models, which is the classical Heisenberg model on the Kagome lattice. So this is this model with antiferromagnetic exchange, classical spins, so and the Kagome lattice. So you probably know that this system actually, if you want to build the ground state manifold of this system, what you have is you first start with XY configuration. It's better to do it this way, and you know that spins must be at 120 degrees one from the others on each plaquette. So if you attach one color to each direction of spins, so each XY ground state is actually 3 coloring, and you can jump from one coloring to another, which are these points here, one coloring to another through loop-like moves. So here you have a 6-site loop move, but you can have much longer loops. So actually, the ground state manifold is massively degenerate. So here it's a discrete degeneracy. And because you can move continuously from one coloring to another, you have a continuous degeneracy. So you have degeneracy is massive and continuous in the ground state. But of course, we have thermal fluctuations. So this is when you're at T equals 0, but when you are at finite temperature, you have this whole spectrum of properties. You are in the paramagnetic regime, then you enter a cooperative paramagnet and a coplanar regime, which means that when you decrease temperature, actually you get rid of those continuous bridges and you just freeze in the XY states, which are 3 colorings of the Kagome lattice. So this is the order out of disorder mechanism, so it's a rich physics. The problem is how you can visualize it. So in condensed matter, we used to do it with S of Q, so it is a static maps of spin-spin correlations. And so you see that when you decrease temperature, you can see that this system enters a Coulomb phase, so it exhibits a pitch points here that you have here. So Coulomb phase described by Christopher Henley. And I remind you that it is a continuous Heisenberg classical antiferromagnet. So this is in S of Q, and of course, these pinch points are the translations, at least at very low temperature, of algebraic but not critical correlations. And still, we cannot observe that in condensed matter. We have to go through the S of Q, right? So it's a bit of a pity. And so we can also look at other properties, like dynamical properties. So when you decrease temperature, you can compute the nonlinear spectrum of the classical nonlinear spectrum of this system. And for instance, if you make a cut at finite frequency, you have this kind of picture where you have ghosts in the excitations, which means if you send a neutron on this model, hopefully one day a sample, there are directions where you won't see the excitations, right? So it's another very peculiar property. So you can see it in S of Q and omega, but the question is, how does it look like in real space? And because it is condensed matter, we can't have a direct look at the excitations. And yes, and of course, and a last observation on this system is, so when you decrease temperature, actually, so you end up in an effective 3-coloring model, and it has very special properties that actually it splits, so it breaks ergodicity, it splits into Kempe sectors, and each Kempe sector also splits into topological sectors, so you have, let's say, some kind of algorithmic transition, and then topological transitions. So all this story tells you that, so here you can measure it very easily in direct space, but again, it's very difficult to see it in reciprocal space. So all this short story, maybe a bit fast, to tell you that, okay, classical physics is very rich, especially in condensed matter, for instance, but the problem is that when you want to probe it, in general, you use this kind of objects. And the problem is that you don't directly visualize what you would like to visualize. And especially many systems are, like Ludovic mentioned, many excitations are the localized excitation, loops-like excitations, or cluster-like excitations. It's very difficult to probe those excitations in reciprocal space. It's better to have them in direct space. You can do in reciprocal space. It will be, because it's localized, it will be flat, you will have a form factor, but you have to do fancy calculations to really know make the correspondence between what you have in direct space and what you have in reciprocal space. So it would be interesting to design equivalent system accessible to optics, say, that you can visualize. So that's the motivation, I mean, from my point of view, of artificial spin ices. I mean, artificial magnets in general. And a side effect, which is a very important one, is that, okay, so we would like to make artificial equivalents of what we cannot probe in condensed matter, what we cannot see, sorry. But maybe we can also make new systems that we cannot be, we will not be able to synthesize in condensed matter. So of course, we are not our community, not me. I've never done anything else but calculations. We are not the first one trying to visualize degrees of freedom. So here I've not made a thorough bibliography, but this is a sketch of few examples. So here you have, for instance, arrays of Josephson junctions, right, in 96. So you see, you can have a XY-like local degree of freedom. So I refer to the poster session of, I think it's Brunner. Yeah, so I don't know if the poster is still available, and it's a bit late. So anyway, so you see that you can just design the geometry and with XY local degrees of freedom. You can also use bitter decoration. So it means that you make superconducting networks. So you have discrete variables, because you have a superconducting network, and then you apply a flux, and you want to make something like, on this lattice, something like an Abrikosov network. So you put flux, quantum of fluxes in those cells, and then you send a magnetic particle that will be trapped in the cell where you have a flux, and you have an Ising-like degree of freedom. So maybe it's not obvious here, but this is an Ising-like Kagome magnet. Equivalent, of course. Then there are also, so these studies have been done in the Institut Néel. Those also, and those are really beautiful, and they have been done by Enrico Liv and Pierre Mollo in '98. So I think it's more or less the XY equivalent of Paola Melado easing-like version of this kind of classical rotor. So we have here an array of classical compass, classical needles interacting in a dipolar way. And this is a quote I took from the abstract, which I think it's very interesting because it refers also to, I think, something that Oleg Chernyshov said about the dissipative character of what happens in these artificial magnets. Here they claim, and I believe them, that they have been able to make a successful mapping of a dynamic dissipative system onto equilibrium statistical mechanics. And this is exactly what we want to do, right? To take statistical mechanics and put it on an artificial magnet. That would be great. And of course, there is this very recent and very well-known contribution of Wang and collaborators, which is now a mesoscopic array of nanoscopic islands. So here you all well know that. So then you can just visualize the magnetism. And so in all previous examples, I want to emphasize that the two-dimensional geometry is fully controllable. For lithography people, it's very easy. You draw something and they print it. So but of course, there are many other issues with respect to this kind of magnetism, this kind of physics. So what are these issues? First, the nature of the local spins, the local pseudo-spins, actually. So because of the dimensions of those objects, which are nanoscopic to mesoscopic dimensions, you have micromagnetic effects. So it's very important. It gives many new degrees of freedom for these objects. There's also the nature of the interactions. So they are of magnetostatic type when they are disconnected. Also, when it's connected, it's a bit different. So, but are there multipolar interactions? So it's very important, of course. And can we model everything by two-body interactions? And actually, it's far from being obvious. And I also quote here the remark of Peter Schiffer saying that making the parallel of those systems with the helium adsorbed on graphite, they are physical systems which cannot be addressed with two-body interactions. They have encoded in their physics the fact that there are multiple interactions. And it might be the case here. And also, and of course, maybe the more crucial point is the type of fluctuations. So we would like temperature if we want to do statistical physics in general. And a priori, those systems are athermal magnets because they have barriers of thousands of kelvins. And a related problem of fluctuation is the spin flip mechanism. How do magnetization reverse during the demagnetization process, for instance? So is it a coherent rotation? Is it a nucleation propagation process? Is it something else? So this has to be properly characterized if you want to proceed with the physics. So the general goal is to have an artificial magnet, to map it ideally in the most controlled way on a statistical physics model, derive the magnetic phase diagram, and play with both and go back and forth between the two of them. So this is our general goal, and this is how we made it. So for us, it was this kind of lattice. So this is a honeycomb lattice, a mesoscopic honeycomb lattice of nanoscopic islands. And so now you all know that. So when you take this geometry, actually, if you draw links between the center of those islands, which is the medial lattice, I guess, you obtain the Kagome lattice, which means that this system is a multi-axis easing Kagome magnet. And because here we are dealing with magnetostatics, at least nearest neighbor interactions are ferromagnetic, which makes sense to say that it's an ice-like physics. So we expect a Kagome ice-like physics, sorry. So here is, for instance, so of course, several people have been investigated this kind of geometry since the first contribution of Wang and collaborators in 2006. And this is a very short and clearly, I guess, not thorough and complete bibliography on the honeycomb geometry only. And here, our main concern will be the role of dipolar interactions. We would like to probe quantitatively the fact that dipolar interactions are essential and that they do appear and they do play a role in this system. And for that, we will start actually with the two first papers of this bibliography of Key and collaborators and Mangotti and collaborators. If you look at their results, so you have here for Key and collaborators a connected lattice a mesoscopic lattice of connected islands, right? And so they have taken those notations. So their system, first they have observed for the first time that the system fully complies to the Kagome ice rule. So it's 2 in, 1 out, or 2 out, 1 in configurations. And they have computed, they have measured those correlation coefficients. So C alpha beta, C alpha gamma, C alpha delta, and so forth. And you see that, and this is the result of classical Kagome simulation on the short range ferromagnetic Kagome lattice. And you see that it's fine for the first correlation, which makes sense because the first correlator translates the ice rule. So it has to be, as soon as you are in the spin ice manifold, you have those correlations. And then you see discrepancies between the experimental correlators and the model. So here I will just emphasize those 2 correlators. I will just spend a few time on C alpha gamma and C alpha delta, so those 2 correlators, which are correlators inside an hexagon. So let's go now to the second paper of Mengotti and collaborators, who have made, instead of a huge lattice, a very small lattices of disconnected islands. And you see that when you put several rings, if you have first ring, you want to have a flux closure. So that's a good sign that you want to minimize the dipolar interactions. If you have 2 rings, you close the flux, but in opposite directions. When you have 3 rings, then there's a problem, of course. So what you can do, what you can play, is you take now the Kagome multi-axis magnet or the honeycomb lattice, and you try with a pen and a paper to do that, to maximize the number of flux closure, and you end up with this kind of state, which you have, let's say a plus, if it's the chirality, a +1, minus, plus, minus, and you have frustrated hexagons, which are on a triangular, super triangular lattice. And actually, if you look at this phase, it's a ground state of the dipolar spin ice of this system, of the Kagome dipolar spin ice, which was shown by Müller and collaborators and by Chern and collaborators. So here, don't pay attention to the year here. It's 2011. Actually, the 2 works were concomitant. And they spent 2 years, actually, to precise something in a phase diagram, which has nothing to do with finding the correct ground state. So I try to do my best, but I'm Daltonian, and I have a problem to resolve the small points. So if I point somewhere else, something which is not... So okay, so if you now look at this, so now it makes sense what those 2 correlators. Now you remember this story of the flux closure. So you see that it makes sense that C alpha beta now, because of dipolar interaction, C alpha gamma and C alpha delta should be higher than expected, because you want to enhance the fact that you want to close the flux. So it makes sense that those 2 correlators are higher than expected and then higher than predicted in the short-range spin ice model, and that it's clearly a strong hint that dipolar interactions are really effective in those magnets, artificial magnets. So this is what we have done. I mean, there I did absolutely nothing. So here is the mesoscopic lattice of nanoscopic islands. So this is the fabrication. So this means absolutely nothing to me, except that it's some kind of magic, and so it gives that, and it's okay. And so this is okay. This I understand. So you put cobalt, so layer of cobalt and a very thin layer, and this is the geometry of this lattice. So you have a 500 nanometers from node to node distance here, and you have the volume, so the full aspect ratio of those islands, which are, as you can see here, strongly anisotropic. So this will give you a strongly shape anisotropy, and then intuitively pseudo-easing spin-like behavior. So what they have done, for historical reasons, they use X-beam microscopy to image the system. So they but I was playing with that, and I lost a few minutes. 6. Thanks a lot. Okay, so they have made demagnetization. So they bought a drill. They put the sample on the drill. They did the usual magnetic demagnetization protocol. They found 34 realizations, and then they observed that there is a very good ice rule compliance, 0.6% of defects actually, but those defects always appear at the same sites. So they suspected structural defects. So despite those two defects, they always observe Kagome ice rules. And so what we have done is to estimate the energy of the observed configurations. So we write the energy as the sum of pair interactions, and we split them in a short range part and a long range part. The short range is actually the nearest neighbor part, and then the rest of the energy, the contribution. Of course, this one is, in a sense, irrelevant. As soon as you enter a spinized manifold, it's constant, it doesn't move, right? So, and this one might reveal a very peculiar structure of the spinized manifold, whether it does depend or not on the long-range interactions. Then you take your 34 configurations and you split them in 3 sets, according to whether they minimize well or not the E-long part, so the long-range part of the interactions. And what you see here, so this is our correlations. So the blue set, green set, and the red set. And you see that the lower the dipolar energy, the long-range energy, the higher those two coefficients. So it makes sense. I mean, 5 correlators are almost E-long independent, but 2 are very sensitive, and these are precisely the 2 correlators that would actually exhibit the way that you want to close the flux in a cell. But maybe it's a tautology. Why? Because actually, what you could do is simulate a short-range spin-ice model. You take 34 configurations of the short-range spin-ice, and then you, of course, they won't be equivalent. And then you can split them the same way we did, so according to whether they minimize the long-range energy. If you do that, of course, you will find that the 2 correlators will be much higher than expected in the set that will minimize the E-long energy. So you might say that we find what we wanted to find, but it's not true, and I show you now. So first, would be the dipolar spin-ice model more suited? So because I'm running out of time, the answer will be yes. And first, so you use micromagnetic simulation to say like ab initio approach of the exchange couplings between islands. And you see that if you look at the theoretical point-like dipole approximation and the micromagnetic couplings, so all couplings are more or less well described by the point-like approximation, but the nearest neighbors. So you just artificially enhance the nearest neighbor in your model, and then you do a Monte Carlo simulations. And you see here all the correlations as a function of temperature. So here, when you go from the paramagnetic to a first spin-ice phase, and this is the short-range model. So in the short-range model, the 2 correlators, alpha gamma and alpha delta, remains constant, while in this case, they do vary. So this points towards that the dipolar spin-ice model is much better to describe this system, this artificial magnet. So I didn't put it there, but of course, when you enter this, these curves were obtained using a loop-like algorithm. If you just put the stochastic dynamics with a single spin flip dynamics, then you will have a strong strong drop of the acceptance ratio, which means that when you enter with the dipolar spin-ice model, when you enter the low temperature regime, you enter the dipolar spin-ice manifold, and you freeze algorithmically. So you can't go to low temperature with a single spin flip algorithm. So this proves that actually the experimental data statistics. The experimental data are compatible with the dipolar spin-ice model, but doesn't prove that the short-range spin-ice statistics are incompatible with the data. So to do that, we have computed the charge-charge correlation. So at each vertex of the honeycomb lattice, you can add the charges of the fractionalized spins, pseudo-spins. So the charges in a spin-ice manifold are either +1 or -1. And what has been shown by Chen and collaborators is that actually at low temperature, there is a second spin-ice manifold in which spin fluctuates through loop-like moves, but charge have crystallized. So that means that actually in this model, you should expect that the nearest neighbor correlator between charges should reach -1, which we see in the simulations. So we can compute the charge-charge correlation in the dipolar spin-ice model and in the short-range spin-ice model. So you see that in the short-range spin-ice model, you have a -1/9 value that I think was quoted by Paulo on Wednesday, which can be very easily calculated. And you see that there is also a distribution of values in the short-range spin ice. So because charge are fluctuating, positions are fluctuating, the correlators is distributed according to a Gaussian distribution, almost Gaussian, with very light tails. So there are no extreme events in a short-range spin ice regime. There are no extreme events of charge-charge correlations. And when you look at the experimental data, you find them, their histogram, you see clearly that they cannot be accounted for by the distribution, the statistics of the short-range spin ice model. So this is why I come to my conclusion, and I hope I have convinced you that clearly this system, this mesoscopic honeycomb lattice of disconnected nanoscopic islands is a frozen, algorithmically frozen Kagome dipolar spin ice with an emergent classical signature of a magnetic charge crystal. So what are the perspectives of this work? First, we would like, of course, as many I think, get closer to the spin ice 2 regime. So what would be the route what would be the way? So first, overcome the algorithmic freezing. So maybe play with the geometry of the lattice and of the islands. Maybe also play with the demagnetization process. So to really do that quantitatively, we think in our group that we should first properly characterize the islands through their Stoner-Wolfart asteroids, and maybe without guess other practical protocols to get to lower temperatures. More generally, is there an equivalent, experimental equivalent of loop-like moves? I don't know. This is, I guess, an open question. If you have a solution, I would be interested. And of course, we want to have a better understanding of micromagnetic degrees of freedom. We say, okay, it's using pseudo spins. It's not totally true, actually, because of micromagnetic degrees of freedom. And for instance, we have shown with micromagnetic simulations that two-dimensional Kagome monopoles, which so when you have 3 in spins or 3 out, so plus or minus 2 charges with respect to the vacuum, actually they have a chirality. I'm sorry. So which means that there are Z2, Z2 objects, not only Z2 objects. And so this might be just for fun because maybe they don't interact, but actually chiralities interact one with the others. A plus plus and a plus minus, it's not the same energy. So they do interact, so it's a relevant parameter, so maybe it will increase the degeneracy, and this is what we like when we are frustrated. We like degeneracy. So maybe it opens the way to model-like approaches, so maybe just put at hand the chirality in classical models, see what emerges from that, whether there is a richer structure of the spin in the spin ice manifolds, and maybe we can manipulate this chirality. And I guess this is time for me to thank you for your attention.
Well, it's not here.
Oh, sorry.
It's not very clear to me. As you found, the nearest neighbor interactions is still important to model the system, or only dipole interaction?
Actually, when you the nearest neighbor interaction, of course, it's important. But let's say if you take it ferromagnetic or antiferromagnetic, there will be a threshold for which it will change the physics. And if you look at the paper of Chern and collaborators, also the paper of Muller and collaborators, then I think so. When you look at the specific heat and the entropy plateaus, so you will see the same values, but of course the range in temperature of the spin ice is the existence of the spin ice is manifold will be driven by the intensity of J1. So if you take here J1 is actually 5 times what it would be in the point-like approximation. If you take J1 equal to 1,000, you will have the same qualitative behavior, but just this phase will range from this point to this point, right? So, yeah, is it what you want to do?
Because, I mean, if you take finite islands that are not connected, then I would not expect a kind of exchange interaction between islands.
Okay.
That's why I'm
but maybe there's a misunderstanding. This exchange here is a pseudo exchange, right? It has nothing to do with condensed matter.
Okay.
It's magnetostatics, and there is no. But okay, so there are 2 points, 2 aspects. So first, it has nothing to do with the the local exchange inside the cobalt nano islands. But even though they were connected, the effective exchange could be has a meaning, even though you would have domain walls whose shape would be dictated by the local exchange. I'm not sure I'm clear, but anyway, in all cases, these effective exchanges are just a translation, sorry, of the fact that these objects are interacting, whether or not they are connected. Right.
Okay, thank you.
So if you saturate the Kagome in one single direction, you get perfect charge order.
That's right.
That is just piggybacking on the spin order.
Mm-hmm.
And so when you do these demagnetization routines with rotating field, they're always imperfect. So you have a tendency to have small ferromagnetic domains. So in your experiment, can you distinguish between a sort of charge order which is just piggybacking on these small ferromagnetic domains from like a true dipolar spin ice model?
I think if you really want to, I think if you want to really make the difference between accidental charge ordering or a real charge ordering which is driven by the demagnetization protocol, you must have a look at the statistics of the of the correlated statistics. So that would be the structure factor of the charge-charge correlations. And so we have not done that, but clearly it's a good point. But I think it's not what we observe.
Okay, thank you. Sorry, could I ask a follow-up? So in your 34 demagnetization routines,
yes,
some are different arrays and some are the same array again and again. Do you get different correlators when you go to a specifically different array to when you just re-demagnetize the same array?
So I did not make the experiments. I guess these 34 demagnetization were on the same array actually. That's why there is only 34 realizations.
Okay, I thought there were a few different samples.
There are different samples, but it was not, I mean, not for this problem of statistics.
Okay.
So what we did also is to increase statistics, but I have not presented here, is to put several masks on in sample and then study it independently.
Okay, thanks.